In the deepest darkness, where galaxies should gather, James Webb found something impossible. Ancient black holes burning alone, no fuel, no neighbors, just void. Scientists analyzed 20 years of cosmic measurements and discovered we are not in the universe we thought. We live inside a bubble, a 2 billion light-year wide pocket of almost nothing. This void is growing, and it is warping everything we measure about reality itself. If you enjoy discovering what lies beyond our cosmic neighborhood, consider subscribing to join us on this journey. Prepare yourselves. We begin. The James Webb Telescope pointed at a region of space 13 billion light-years away and found something that broke every model. 5 ancient quasars, blazing with the power of trillions of stars, floating in what appeared to be cosmic deserts. These objects formed when the universe was barely 430 million years old. That timeline alone challenged physics. Quasars need supermassive black holes at their cores. Black holes need matter, lots of it. Gas, dust, entire galaxies feeding the gravitational beast at the center. Theory predicted these early quasars would sit in the densest neighborhoods of the young cosmos, surrounded by 50 or more companion galaxies providing fuel for their fires. Scientists at MIT led the observation campaign in 2024. They examined the cosmic surroundings of each quasar field. Some matched predictions perfectly. Crowded environments, packed with galactic neighbors, exactly as models suggested. Then came the others. These quasars drifted in isolation. Only a handful of stray galaxies scattered nearby. No dense environment. No obvious fuel source. Christina Eilers and her team checked their data 3 times. The findings held. Lonely, supermassive black holes, shining impossibly bright in regions where they had no right to exist. This discovery is confirmed through multiple observations. The telescope's instruments captured clear images of these isolated regions. Each observation session revealed the same pattern. Dense quasar fields where expected, empty quasar fields where impossible. The discrepancy forced physicists to question fundamental assumptions about how black holes grow. Without surrounding matter to consume, these objects should have stayed small. Instead, they achieved masses millions of times greater than our home star in a cosmic instant. The location of these lonely quasars suggested something stranger than random distribution. They appeared to inhabit voids, vast regions of space with below-average matter density. Voids were known to exist in the modern universe. Finding them in the infant cosmos, already large enough to isolate quasars, contradicted structure formation timelines. The universe at that age should have been more uniform. Gravity had not yet pulled matter into the extreme concentrations and depletions observed today. The team published their findings in the Astrophysical Journal in October 2024. Their conclusion remained cautious yet clear. These quasars exist in environments that current theory cannot explain. Either black hole growth operates through unknown mechanisms, or the early universe contained structure on scales previously thought impossible. Both possibilities rewrote cosmology. Neither provided comfort. Because what Webb found at the edge of the observable universe might also exist right here, wrapped around our own galaxy. Your home galaxy floats inside a bubble of nearly empty space, 2 billion light-years across. The Keenan-Barger-Cowie void, named after the 3 astronomers who first identified it in 2013, surrounds the Milky Way like an invisible sphere. This structure is confirmed through galaxy number counts across multiple wavelengths. Optical telescopes, infrared surveys, X-ray observations, radio measurements, all point to the same conclusion. Our local universe contains 20% less matter than it should. Picture the cosmos as an ocean. Galaxies cluster into islands and archipelagos connected by bridges of matter. These structures form the cosmic web, a network spanning the entire observable universe. Between the dense filaments lie voids, the open water between island chains. Most galaxies live on the islands or bridges. We live in the middle of the ocean. The KBC void is not the only empty region in space. Thousands of voids have been mapped throughout the universe. This one is different. It ranks among the largest ever detected. More importantly, we sit close to its center. The discovery emerged from near-infrared surveys that counted galaxies at increasing distances from Earth. Close by, galaxy density appeared normal. As astronomers pushed their surveys farther out, reaching 200 million light-years, then 400 million, then 600 million, something became clear. The number of galaxies per unit volume increased steadily with distance. We occupy a region significantly underdense compared to the cosmic average. The deeper into space telescopes looked, the more obvious the discrepancy became. This finding is confirmed by multiple independent research teams using different methods. The 2 Mass Redshift survey catalogued over 43,000 galaxies within 380 million light-years. The pattern held: fewer galaxies nearby, more galaxies farther away. The distribution matched predictions for an observer inside a supervoid. Additional observations from the Sloan Digital Sky Survey and WISE infrared mission reinforced the conclusion. Our cosmic neighborhood is authentically sparse. The void overlaps with the Laniakea supercluster, a structure containing 100,000 galaxies, including our own. At first, this seems contradictory. How can a supercluster exist inside a void? The answer lies in scale. Laniakea spans 500 million light-years. The KBC void spans 2 billion. The supercluster represents a relatively dense region within an overall underdense volume. Think of it as a small island in the middle of the Pacific, still surrounded by vastness, still fundamentally isolated. The implications of this location extend far beyond simple geography. Living inside a void changes how we measure the universe itself. 2 groups of astronomers measure the same thing and get answers that refuse to match. The Hubble constant defines how fast the universe expands. It tells us the rate at which space itself stretches, carrying galaxies apart. This number is not optional in cosmology. It determines the age of the universe, the distribution of dark energy, the timeline of cosmic evolution. Everything depends on getting it right, yet the methods to measure it keep returning conflicting values. The first approach studies the cosmic microwave background, ancient light from 380,000 years after the Big Bang. This radiation carries imprints of the infant universe, patterns frozen into the sky when atoms first formed. Detailed analysis of these temperature fluctuations reveals an expansion rate of approximately 67 kilometers per second per megaparsec. The Planck satellite measured this value with exceptional precision. It matches predictions from the standard cosmological model almost perfectly. The second method examines nearby galaxies. Astronomers identify Cepheid variable stars which pulse with predictable brightness based on their true luminosity. By comparing apparent brightness to actual luminosity, distances can be calculated. These distance measurements extend to galaxies hosting type Ia supernovae, explosions that serve as standard candles across cosmic distances. This local measurement technique, refined by Adam Rees and his team using both Hubble and James Webb data, produces a different answer: approximately 73 kilometers per second per megaparsec. 10% higher than the cosmic microwave background method. 10% sounds modest. In cosmology, it represents a crisis. The tension has grown stronger as measurements improved. Early observations left room for error bars to overlap. Modern precision eliminated that comfort. Both techniques have been checked, rechecked, and validated through independent observations. The James Webb Telescope confirmed the distance ladder measurements Hubble began. No systematic errors explained the gap. No instrument calibration issues resolved the conflict. The numbers simply refused to agree. This discrepancy is confirmed and has persisted for over a decade. Nobel laureate Rees stated that as measurements grow more precise, the tension does not disappear. It deepens. If local measurements are accurate, the universe could be roughly 1 billion years younger than currently calculated. Galaxy formation timelines shift. Dark energy behavior changes. The entire structure of cosmic history requires revision. If cosmic microwave background measurements are accurate instead, then something unknown accelerates expansion in our local region, something affecting all nearby distance measurements. Either way, our understanding of the universe contains a fundamental flaw. But what if the answer is not in our measurements? What if the answer is in where we are measuring from? Before atoms existed, the universe was a screaming plasma of particles and energy. Photons, electrons, protons, and dark matter churned together in a searingly hot fluid. Pressure waves rippled through this cosmic soup, generated by tiny density fluctuations from quantum events in the first moments after creation. These waves traveled outward at nearly half the speed of light, compressing matter as they moved. Then, 380,000 years after the Big Bang, everything changed. The universe cooled enough for electrons and protons to combine into hydrogen atoms. Light broke free. The waves froze in place. Those frozen sound waves left their signature in two places. First, in the cosmic microwave background radiation itself, visible as subtle temperature variations across the sky. Second, and more importantly, for void detection, in the distribution of matter throughout space. Regions where waves compressed matter became slightly denser. These overdense zones attracted more material through gravity over billions of years, eventually forming the galaxy clusters and filaments we observe today. The distance between compressed regions, roughly 490 million light-years in today's expanded universe, became a cosmic ruler. Astronomers call these patterns baryon acoustic oscillations. This cosmic ruler works because the distance is fixed by physics. Sound waves could only travel so far in the time before atoms formed. That maximum distance, called the sound horizon, provides a standard length scale imprinted across the entire universe. By measuring how large this scale appears in galaxy surveys at different distances, cosmologists can determine both how far away those galaxies are and how fast space was expanding at different times in cosmic history. It is confirmed and serves as one of the most reliable tools in modern cosmology. The Dark Energy Spectroscopic Instrument, or DESI, conducts the most detailed surveys of these oscillation patterns. The telescope measures positions and redshifts for millions of galaxies. Redshift indicates how much space has expanded since light left each galaxy, providing a distance measurement. When plotted, galaxies show a subtle preference for certain separations. They cluster more strongly at multiples of that 490 million light-year scale. The pattern appears weak in small samples, but emerges clearly when millions of galaxies are analyzed together. Recent DSE observations revealed something unexpected. The baryon acoustic oscillation measurements do not perfectly match predictions from the standard cosmological model. At low redshifts, meaning closer distances, the apparent expansion rate rises above expectations. At high redshifts, farther away, measurements align with cosmic microwave background predictions. Something creates a systematic shift in nearby observations. The data published in 2025 showed this deviation concentrated in specific redshift ranges. Two particular distance bins drove most of the anomaly. Cosmologists proposed various explanations: time-varying dark energy, modifications to gravity, unknown systematic errors in the surveys. But there was another possibility that few wanted to consider. What if the measurements were accurate and we simply live somewhere special? Scientists from the University of Bonn and St. Andrews compiled 20 years of baryon acoustic oscillation data. They modelled what these measurements should look like if Earth sits inside a massive underdense region. Then they compared those predictions to actual observations. The results were not subtle. Models including a local void fit the data 100 million times better than models assuming uniform matter distribution. This finding is confirmed through rigorous statistical analysis published in the monthly notices of the Royal Astronomical Society in 2025. The analysis focused on a specific measurement called D sub 5, which combines distance information in a particular way that averages angular and radial measurements together. In a perfectly uniform universe expanding according to standard cosmology, this quantity should follow a smooth curve as observers look to greater distances. The compiled observations show something different. At redshifts below 0.3, corresponding to distances within roughly 4 billion light-years, the measurements systematically deviate from predictions. The observed D sub V values appear larger than expected, exactly the pattern a local void would create. The mechanism works through gravitational dynamics. Inside an underdense region, matter experiences attraction toward the denser material outside. This creates bulk flows, where galaxies move away from the void center faster than pure cosmic expansion would drive them. These peculiar velocities add to cosmological redshift. When astronomers observe a galaxy and measure its redshift, they assume all motion comes from space expanding. If the galaxy has additional outward velocity from void outflows, its redshift appears slightly higher. This inflates distance estimates. The baryon acoustic oscillation scale, which has a known physical size, appears stretched across the sky. The D sub V measurement increases. The researchers tested 3 different density profiles for the void: Maxwell-Boltzmann distribution, Gaussian distribution, exponential distribution. All 3 improved the fit compared to no void, though the Gaussian profile performed best. The statistical measure used to quantify agreement, called chi-squared, dropped from 75.7 in the uniform model to between 47 and 51 in the void models. This represents a reduction in tension from 3.3 sigma to between 1.1 and 1.4 sigma. In statistical terms, the uniform model is as unlikely as flipping a coin and getting heads 13 times in a row. The void model is as likely as getting heads twice in a row. A separate analysis examined how quickly the apparent cosmology returns to standard predictions at high redshift. Any local solution to the Hubble tension must eventually give way to global behavior as observations extend far beyond the void. The model predictions show exactly this transition. At low redshift, dominated by void dynamics, the expansion appears faster. At high redshift, beyond the void's influence, measurements converge with cosmic microwave background expectations. The transition occurs smoothly across the tested range. but statistics alone do not capture the full story. Physical evidence from galaxy motions confirms the void in even more direct ways. Galaxies inside underdense regions move differently than their cousins in normal space. The Milky Way itself rushes away from the void center at 600,000 miles per hour. This peculiar velocity, confirmed through measurements of our motion relative to the cosmic microwave background, far exceeds typical galaxy speeds in denser environments. The void does not push us, the matter outside pulls. Gravity from surrounding filaments and superclusters creates a net force drawing everything outward from the void's interior. The phenomenon is called bulk flow. Astronomers measure it by observing many galaxies within a spherical volume centered on our position and calculating their average velocity. The Cosmic Flows project catalogues these motions using various distance measurement techniques. The fourth iteration of this catalogue, released in 2023, includes redshift-independent distances for thousands of galaxies. When analysed together, they reveal the Milky Way participates in a large-scale streaming motion. The observed bulk flow curve rises with distance to about 250 megaparsecs, reaching speeds roughly 4 times higher than standard cosmological models predict. This discrepancy is confirmed and presents another challenge to the uniform universe picture. In a smooth cosmos where matter distributes evenly on large scales, bulk flows should decrease as survey volumes grow. Random motions from local structures should average out. Instead, the flow strengthens as more distant regions get included. Sergej Mazurenko and colleagues demonstrated in 2024 that void models naturally explain this behavior. Material streaming out of an underdense region maintains coherent motion across enormous volumes. The KBC void parameters that fit the Hubble tension also predict bulk flows matching observations. The velocity field exhibits specific features tied to void geometry. Galaxies near the void center move outward in all directions. As distance from center increases, outflow speeds decline. Eventually, at the void boundary, roughly 1 billion light-years away, the expansion rate returns to cosmic average. Beyond that point, gravity from denser regions dominates. The transition zone, where void dynamics fade, creates complex patterns of motion. Some galaxies accelerate toward nearby attractors, like the Shapley concentration. Others flee from relative voids, like the dipole repeller. Our location experiences both influences simultaneously. The local sheet, a flattened distribution of galaxies that includes the Milky Way, represents one wall of a smaller void structure nested within the larger KBC void. This smaller void, sometimes called the local void, extends approximately 200 million light-years and sits adjacent to our position. Galaxies in the local sheet rush away from its center at 160 miles per second. The effect resembles water draining from a bowl. Matter flows preferentially out of voids and accumulates along their boundaries, creating the sheets and filaments of the cosmic web. We inhabit one of these transitional zones, watching cosmic drainage happen in real time. And the forces shaping our motion have been at work since moments after creation. 13 billion years ago, when starlight first ignited in the primordial darkness, something was already feeding. Supermassive black holes existed less than 1 billion years after the Big Bang. The James Webb telescope detected several with masses exceeding 1 billion times our home star. J0305-3150, one quasar studied by the Aspire program, outshines its entire host galaxy despite existing only 830 million years after creation. This timeline presents a devastating problem for theory. Black holes grow by consuming matter. Standard growth models involve 2 stages. First, a seed black hole forms from the collapse of massive early stars. These seeds start small, perhaps 100 times the mass of our home star. Second, the seed accretes gas from its surroundings over time. Accretion has limits. Matter falling into a black hole heats up and radiates energy. This radiation pushes back against infalling material, creating a natural throttle on growth rate. Even under optimal conditions, a black hole can only roughly double its mass every 50 million years through this process. Run the numbers backward. A 1 billion solar mass black hole detected at 800 million years after the Big Bang had only that much time to grow. Starting from a 100 solar mass seed requires doubling mass 20 times. 20 doublings need 1 billion years at maximum accretion rate. The timeline does not fit. These objects achieved their observed masses faster than physics allows through conventional feeding. Something else happened. Two possibilities emerge. Either the seed black holes started much heavier than stellar collapse produces, or they grew through mechanisms beyond standard accretion. The first scenario involves direct collapse black holes. In rare conditions during the early universe, massive clouds of primordial hydrogen might collapse directly into black holes without forming stars first. This process could produce seeds of 10,000 to 1 million solar masses, providing a substantial head start. The second scenario invokes super Eddington accretion, where black holes somehow consume matter faster than radiation pressure should permit. Both mechanisms remain theoretical. Neither has been confirmed through a direct observation. Roberto Maiolino's team using Webb found additional evidence suggesting unusual black hole growth. They detected extremely dense gas near these early quasars, consistent with rapid accretion. They also observed powerful winds being expelled from the systems at tremendous velocities. These winds carry matter away from the black hole, even as other material falls in. The combination indicates violent, chaotic feeding processes unlike anything seen in the modern universe. The quasars appear to be growing in desperate bursts, consuming whatever fuel exists in their sparse environments. Some scientists proposed these objects inhabit regions that later evolved into the voids we observe today. Early overdensities that allowed rapid black hole formation, followed by expansion and evacuation of surrounding matter. Testing this hypothesis requires understanding how voids themselves form. The KBC void contains galaxies, stars, dark matter, and ordinary matter. It is not a true vacuum. The term void describes relative density, not absolute emptiness. Matter concentration in the void measures approximately 80% of the cosmic average according to some studies. Other analyses suggest densities as low as 50% of average. The discrepancy depends on how far observations reach beyond the void boundary and how results are normalized. All measurements agree on one point. Our region is significantly underdense compared to typical cosmic neighborhoods. This 20% deficit in matter density creates enormous consequences. Gravity weakens in underdense regions. With less mass pulling inward, the expansion of space encounters less resistance. Imagine a balloon inflating inside a room. In one corner, heavy weights hang from strings attached to the balloon surface. In another corner, lightweight strings barely tug. The balloon stretches faster where resistance is weakest. The universe behaves similarly. Regions with below average matter density expand slightly faster than average. Regions with above average density expand slightly slower. The effect accumulates over cosmic time. For observers inside an underdense region, this creates a systematic bias in measurements. When astronomers calculate the Hubble constant using local galaxies, they sample an environment expanding faster than the global average. The measured expansion rate appears elevated. This explains why local measurements using Cepheids and supernovae return higher values than cosmic microwave background predictions. Both measurements are accurate, they simply probe different environments. The cosmic microwave background reveals global average expansion. Local measurements reveal expansion within our peculiar location. The mechanism remains confirmed through multiple lines of evidence. Computer simulations of structure formation in the universe naturally produce voids with properties similar to the KBC void. These simulations start from initial conditions matching cosmic microwave background observations and evolve forward using known physics. Voids emerge as inevitable features of gravitational structure formation. Matter clusters together under its own gravity, leaving evacuated regions behind. The simulations predict voids should occupy roughly 70% of the universe's volume, despite containing only a small fraction of galaxies. Observations of distant quasars gravitationally lensed by foreground matter distributions provide another test. Lensing strength depends on the total mass along the line of sight between observer and quasar. Studies have found some sight lines show weaker lensing than average, consistent with passing through underdense regions. The distribution of lensing strengths across the sky matches predictions from large-scale structure surveys showing void and filament networks. We are not special in living near a void. We are special in how large our void is, and in how it affects our view of cosmic truth. But measuring darkness requires understanding what fills the bright spaces in between. 100,000 galaxies stretch across 500 million light-years, in a structure named Laniakea, meaning immeasurable heaven in Hawaiian. The Milky Way occupies one small corner of this vast system. Laniakea includes the Virgo supercluster, the Hydra Centaurus supercluster, and the Pavo-Indus filament. All these galaxies share a common motion, flowing together toward a central basin of gravitational attraction. Detailed surveys mapping this structure, published by Brent Tully and colleagues, revealed the Laniakea boundaries in 2014. The discovery seemed to establish our cosmic neighborhood as a major feature of the universe. Then came the realization that changed interpretation. Laniakea sits inside the KBC void. The entire supercluster, with all its galaxies and matter, occupies an overall underdense region of space. This creates a paradoxical situation. How can a massive concentration of galaxies exist within a void? The answer involves scale and context. Laniakea represents the densest region within a larger underdensity. Think of it as a mountaintop in a valley. The peak rises above its surroundings locally, but remains lower than peaks in adjacent mountain ranges. The void does not eliminate structure completely. It suppresses the average density across enormous volumes. The gravitational dynamics within Laniakea reflect void influence. Galaxies stream toward the Great Attractor, a concentration of mass near the center of Laniakea. Simultaneously, the entire supercluster participates in the outflow from the KBC void center. These motions combine. Our galaxy moves toward the Shapley concentration, a massive cluster of galaxies beyond Laniakea's edge. We also move away from the dipole repeller, an underdense region on the opposite side of the sky. The repeller does not push. It simply fails to pull as strongly as surrounding matter. The combined effect creates our peculiar velocity through space. Recent analysis suggests Laniakea might not be gravitationally bound. The outflow from the void may overcome the supercluster's internal gravity, preventing it from collapsing into a single structure over cosmic time. If true, Laniakea represents a transient feature. Galaxies that appear grouped together today will disperse as the void continues expanding. This challenges the notion that superclusters represent stable, long-lived structures. Instead, they may be temporary concentrations within larger evacuation flows. The void's influence extends beyond motion to affect galaxy properties. Studies comparing void galaxies to their counterparts in denser regions found systematic differences. Void galaxies tend to be smaller, bluer, and younger. They form stars more actively, despite having less available gas. This phenomenon is confirmed across multiple void samples throughout the universe. The explanation involves environmental effects. In dense regions, galaxies frequently interact and merge. These violent encounters can shut down star formation as gas gets heated or expelled. In voids, galaxies evolve in relative isolation. They retain their gas supplies longer and continue forming stars steadily. Our location in an underdense region may have influenced the Milky Way's evolutionary history, and the forces that created our void have been shaping the cosmos since the first fraction of a second after creation. In the beginning, space was almost perfectly smooth. Quantum fluctuations during cosmic inflation created tiny density variations, 1 part in 100,000. Regions slightly denser than average contained minutely more matter. Regions slightly less dense contained minutely less. These differences, microscopic at first, held the seeds of all future structure. Gravity amplified the variations. Dense regions attracted more matter, becoming denser. Underdense regions lost matter to their surroundings, becoming emptier. The process fed on itself across billions of years. The timeline of void growth follows cosmic expansion history. During the first few 100 million years, matter remained distributed relatively uniformly. The universe had not yet expanded enough for gravitational instability to carve extreme density contrasts. Small voids existed, but remained shallow. Then stars and galaxies began forming in overdense regions. These concentrations exerted stronger gravitational pull on their surroundings. Matter accelerated toward them, draining underdense regions more rapidly. Voids deepened and expanded. The contrast between dense and empty grew more pronounced. Dark energy changed void evolution approximately 6 billion years ago. Before that transition, matter dominated cosmic dynamics. Gravity slowed expansion everywhere, though less effectively in voids than in dense regions. After dark energy became dominant, expansion accelerated. This acceleration affected underdense regions more strongly than dense ones. Where matter concentration was high, local gravity partially counteracted dark energy's push. Where matter concentration was low, dark energy drove expansion with less opposition. Voids began inflating faster. Their boundaries rushed outward into surrounding space. The local void demonstrates this process at smaller scale. It spans approximately 200 million light-years and sits adjacent to the Milky Way. Galaxies forming the local sheet, including our own, flee from this void at 160 miles per second. That velocity exceeds what pure cosmic expansion would produce at such distances. The extra motion comes from gravitational repulsion. Underdense regions create negative pressure gradients. Matter experiences a net force away from the void center, as if pushed by invisible hands. In truth, matter simply falls toward denser regions surrounding the void, but the effect resembles active expulsion. Computer simulations tracking void evolution show they grow primarily through evacuation rather than expansion of existing empty space. As galaxies move toward dense filaments and clusters, they leave behind increasingly sparse regions. The void volume increases as matter redistributes. Eventually, voids reach a characteristic size determined by the balance between gravitational infall and cosmic expansion. The largest void spans several hundred million light-years. The KBC void, at 2 billion light-years, pushes or exceeds this typical scale. Some researchers question whether a void this large can form within standard cosmology. Alternative theories invoking modified gravity suggest structure forms faster than conventional models predict, allowing extreme voids to develop. But regardless of formation mechanism, the void around us shapes our observations in profound ways, including phenomena we cannot observe at all. Imagine the universe as frozen foam. Dense walls surround empty bubbles. Where walls intersect, thick strands form. Where strands meet, massive knots accumulate. This structure, called the cosmic web, organizes all matter across billions of light-years. The walls contain galaxy sheets, the strands contain filaments, the knots contain galaxy clusters, the bubbles are voids. Each component plays a distinct role in cosmic dynamics. Together, they create a pattern resembling neural networks or biological tissue on impossible scales. Galaxy filaments rank among the largest known structures. Individual filaments can stretch 300 million light-years or more. The Sloan Great Wall, discovered in 2003, measures 1.4 billion light-years long. The Hercules Corona Borealis. Great Wall may span 10 billion light-years, though its status as a single coherent structure remains debated. These filaments are not solid objects. They consist of galaxy clusters and groups connected by diffuse gas strands. Matter concentrates along these highways like cities along ancient trade routes. Traffic flows through the network as galaxies fall along filaments toward massive clusters. Walls form where filaments intersect, creating two-dimensional sheets of galaxies. The local sheet demonstrates this feature. It contains the Milky Way, Andromeda, and hundreds of other galaxies spread across a flattened distribution. Walls typically measure 100 to 300 million light-years across, but only 10 to 30 million light-years thick. They separate adjacent voids like the panels of a foam structure. Most galaxies in the universe reside in walls and filaments rather than in clusters or voids. These intermediate density environments host steady star formation and represent the typical galactic habitat. Voids occupy the spaces between walls and filaments. They comprise roughly 70% of the universe's volume, despite containing only a small fraction of galaxies. Typical voids span 30 to 100 million light-years. Supervoids exceed 300 million light-years. The Boötes void, discovered in 1981, stretches 330 million light-years and contains only about 60 galaxies. For comparison, a similar volume in average cosmic space would hold roughly 2,000 galaxies. The emptiness is profound, though not absolute. Recent surveys revealed even larger structures. Baryon acoustic oscillation features create periodic clustering patterns on scales approaching the sound horizon of 490 million light-years. Some apparent structures may represent statistical fluctuations rather than physically connected systems. The debate continues about what constitutes a single structure versus multiple coincidentally aligned features. What remains undisputed is the universe's extreme, large-scale organization. Gravity has carved space into a network of solid and void, full and empty, light and darkness. We inhabit one particular bubble in this foam, watching cosmic drainage in action. And our peculiar location affects not just what we see, but what we can never observe. The universe is either 13.8 billion years old or approximately 10% younger. The age calculation depends on the Hubble constant. Higher expansion rates mean the universe reached its current size in less time. If local measurements showing faster expansion are accurate without accounting for void effects, cosmic age drops to roughly 12.5 billion years. This creates a catastrophic problem. Astronomers have identified stars older than that. Globular clusters contain some of the universe's most ancient stars. Detailed analysis of their light reveals ages exceeding 13 billion years for the oldest specimens. These measurements come from understanding stellar evolution. Stars burn fuel at predictable rates based on their mass and composition. As they age, their surface temperature and brightness follow known patterns. By comparing observations to theoretical models, astronomers determine ages with reasonable precision. The margin of error allows some flexibility, but not enough to compress these stars into a 12.5 billion-year-old universe. If local expansion measurements are correct at face value, either stellar age calculations are fundamentally wrong, or the universe is older than its expansion history suggests. The first possibility seems unlikely, given how well stellar models match other observations. The second possibility makes no sense. A universe cannot be younger than its contents. The paradox forces reconsideration of assumptions. The void hypothesis resolves this tension without exotic physics. It suggests local expansion measurements do not reflect global cosmic history. They reveal local conditions within an underdense region. The universe's true age remains 13.8 billion years, consistent with both cosmic microwave background observations and stellar ages. The resolution works because age calculations depend on integration over cosmic history. Astronomers model how fast the universe expanded during different epochs and add up the time. In standard cosmology, this calculation uses a single expansion rate that applies everywhere. In void cosmology, different regions expand at different rates. The global average expansion matches cosmic microwave background predictions. Local expansion within voids runs faster. Both statements can be simultaneously true. Our measurements see the local enhanced expansion. The universe's age reflects the global average. This framework preserves successes of standard cosmology while explaining the Hubble tension. The cosmic microwave background, anisotropies, the abundance of light elements from primordial nucleosynthesis, the observed large-scale structure, all remain consistent with their current interpretations. Only local distance ladder measurements require reinterpretation as probes of void environment rather than global cosmology. The elegance of this solution appeals to many researchers. It solves multiple problems without invoking new physics or exotic components, but elegance does not equal truth. Alternative explanations for the Hubble tension propose modifications to fundamental laws. General relativity has passed every test for over 100 years. From Mercury's orbit to gravitational waves, Einstein's theory predicts observations with stunning accuracy. Yet it requires dark matter and dark energy to explain the universe we observe. 85% of matter must be invisible. 70% of cosmic energy must be a mysterious field causing accelerated expansion. Some physicists wonder if we are missing something fundamental about gravity itself, rather than inventing invisible components. Modified Newtonian dynamics, proposed by Mordechai Milgram in 1983, changes how gravity works at low accelerations. In regions where gravitational forces are extremely weak, the theory suggests gravity remains stronger than Newton or Einstein predicted. This modification eliminates the need for dark matter in galaxies. Galaxy rotation curves, which standard physics explains through dark matter halos, emerge naturally from the modified force law. The theory also makes testable predictions about galaxy behavior that match observations in many cases. Applying modified dynamics to cosmology requires additional components. Pavel Krupa and colleagues developed a framework called NUHDM that combines modified gravity with sterile neutrinos as a hot dark matter component. Sterile neutrinos have rest energy of about 11 electron volts. They interact weakly with ordinary matter but contribute to cosmic evolution. This hybrid model reproduces cosmic microwave background observations while enhancing structure growth on scales above 100 megaparsecs. Crucially, it allows larger voids to form earlier in cosmic history than standard cosmology permits. Indranil Banik and colleagues showed in 2020 that modified gravity naturally produces the KBC void with observed properties. Their simulations started from cosmic microwave background initial conditions and evolved forward using the modified force law. Voids formed faster and grew deeper than in standard gravity simulations. The resulting structure matched galaxy surveys showing local underdensity. The same models predicted bulk flow velocities consistent with cosmic flow's observations. Without the modified dynamics, producing a void as large as the KBC within standard cosmology appears difficult. Multiple studies suggest such a structure has less than 1% probability of existing in a universe governed by Einstein's equations. The debate remains unsettled. Modified gravity theories face their own challenges. They struggle to explain some gravitational lensing observations, where light bending appears stronger than modified dynamics predicts. The bullet cluster, where two galaxy clusters collided, shows offset between visible matter and gravitational lensing that matches dark matter explanations better than modified gravity. Proponents argue these systems require additional physics beyond the basic modified theory. Critics consider such adjustments as ad hoc, as adding dark matter itself. What both sides agree on is that something fundamental remains misunderstood, either about the universe's composition or about gravity's behavior. The void around us might hold clues to which. Detecting an underdensity around your own position presents a unique challenge. Astronomers cannot step outside the universe and look back at our location. All observations must be made from within the structure being studied. This creates systematic blind spots. Measuring local galaxy density requires comparison to cosmic average density. Determining cosmic average requires surveying vast volumes. Surveys originating from inside an underdense region will initially sample primarily underdense space. Recognizing the discrepancy demands reaching far enough to escape local effects. Early galaxy surveys lacked the depth to reveal the void. The Harvard Center for Astrophysics Redshift survey in the 1980s catalogued galaxies within a few 100 million light-years. This pioneering work discovered cosmic structure, including smaller voids and filaments. It established that galaxies do not distribute uniformly, but cluster into patterns. However, its limited range prevented recognition of the much larger KBC void. Detecting a 2 billion light-year structure requires observing well beyond its boundaries. Surveys reaching only 300 or 400 million light-years sample mostly void interior. The breakthrough came from near-infrared observations. The 2-micron all-sky survey, or 2MASS, mapped galaxies at wavelengths where dust obscuration is minimal. This allowed penetration into regions of the sky where optical surveys struggled. The 2MASS redshift survey followed up by measuring distances to over 43,000 2MASS galaxies. Published data extended to approximately 380 million light-years. Analysis by Keenan, Barger, and Cowie in 2013 revealed the critical pattern. galaxy number density increased systematically with distance from Earth. The finding faced skepticism initially. Could the pattern represent a selection effect or systematic error in the survey? Subsequent analysis using independent datasets confirmed the result. Observations at other wavelengths, including optical, X-ray, and radio, all showed consistent underdensity. The Sloan Digital Sky Survey, which mapped millions of galaxies across large areas of sky, supported the conclusion when analyzed specifically for local density. By 2017, multiple independent teams agreed Earth's cosmic neighborhood is authentically underdense compared to typical regions of the universe. Even with confirmation, interpreting the significance took time. Early papers focused on simply describing the void structure. Connecting it to the Hubble tension emerged gradually as measurements of the expansion rate discrepancy grew more precise. The realization that our peculiar location might explain cosmology's biggest puzzle gained traction only in the past few years. The void was hiding in plain sight, not through some property of the void itself, but through the difficulty of recognizing your own location's abnormality when you cannot observe from anywhere else. And the void's existence traces back to patterns frozen into space during the first moments of creation. 1/1,000,000,000 of a trillionth of a trillionth of a second after the Big Bang, quantum fluctuations rippled through the inflating universe. These fluctuations, generated by fundamental uncertainty in quantum fields, created tiny variations in energy density. Inflation, the rapid exponential expansion of space during the universe's first fraction of a second, stretched these microscopic quantum ripples across cosmic distances. By the time inflation ended, the fluctuations spanned millions of light years. They provided the seeds for all subsequent structure formation. The pattern of these primordial fluctuations appears in cosmic microwave background observations. The Planck satellite mapped temperature variations across the entire sky to millionth of a degree precision. Hot spots correspond to slightly denser regions in the early universe. Cold spots correspond to slightly less dense regions. The statistical properties of these variations match predictions from quantum field theory during inflation. The amplitude of fluctuations, the spectrum of sizes, the slight deviation from perfect randomness all align with theoretical expectations. This agreement ranks among the most successful predictions in physics. From these initial density variations, gravity carved the present universe. Overdense regions attracted surrounding matter. As material flowed inward, these regions became more overdense. The process accelerated. Small density enhancements grew into protogalaxies. Protogalaxies merged into galaxies. Galaxies clustered into groups. Groups aggregated into clusters. Clusters connected along filaments. Filaments outlined voids. The entire cosmic web emerged from amplification of quantum noise stretched to astronomical scales. Underdense regions underwent inverse evolution. Starting with slightly below average density, they lost matter to surrounding overdensities. As material drained away, local density fell further below average. The process created expanding bubbles of relative emptiness. Early voids were shallow. Over billions of years, they deepened as matter continued evacuating. The largest voids trace back to the largest initial underdensities in the primordial quantum fluctuation field. These rare, extreme deviations in the early universe grew into the supervoids we observe today. The KBC void's existence implies an unusually large underdensity in the quantum fluctuation field that happened to overlap with our location. Statistically, such features must exist somewhere in a large enough universe. The question is whether finding ourselves in one is surprising. some researchers argue it is not. The universe extends far beyond our observable region. Somewhere, extreme fluctuations must occur. We observe from where we happen to be. Others suggest the void's size pushes or exceeds what standard inflationary models naturally produce. If true, it might indicate inflation, operated slightly differently than current theory describes, or it might simply represent a rare but allowed fluctuation. Either way, the void enclosing our galaxy began as quantum uncertainty at the smallest scales, expanded to cosmic proportions by inflation, and amplified through billions of years of gravitational evolution. And its continued growth depends on the most mysterious component of the universe. Dark energy makes up 68% of the universe's total energy density according to current observations. Unlike matter, which attracts gravitationally, dark energy drives cosmic expansion. The current standard model treats dark energy as a cosmological constant, a uniform energy density filling all space. This simple model matches most observations. However, dark energy's influence on structure formation depends on environment. In regions dominated by matter concentration, gravity overwhelms dark energy's push. In regions where matter is sparse, dark energy dominates dynamics. Voids represent dark energy-dominated environments. With below-average matter density, gravitational forces weaken. Dark energy's accelerating effect faces less resistance. Space expands faster in void interiors than in dense regions. This differential expansion rate creates the peculiar velocity patterns observed in galaxy surveys. Matter streams from voids toward filaments, not because voids actively push, but because dark energy accelerates expansion more effectively where opposition is weak. The resulting dynamics resemble repulsion, though the underlying mechanism is uncoupled from matter distribution. The shape evolution of voids provides insights into dark energy properties. If dark energy density stays constant over time, as the cosmological constant model assumes, voids should expand at rates matching specific predictions. If dark energy density changes with time or varies with environment, void expansion would differ. Measuring void shapes across cosmic history tests these scenarios. Recent observations from the Dark Energy Spectroscopic Instrument include data suggesting possible time variation in dark energy density. The statistical significance remains modest, and alternative explanations exist. But if confirmed, it would revolutionize cosmology as profoundly as discovering dark energy itself in the late 1990s. Within voids, dark energy affects galaxy evolution in subtle ways. Galaxies forming in underdense environments experience less gravitational harassment from neighbors. They avoid frequent close encounters that strip gas or trigger starbursts. This isolation allows void galaxies to evolve more peacefully than their counterparts in dense regions. Observations confirm void galaxies tend to be gas-rich, actively forming stars, and less likely to have evolved into passive elliptical forms. The Milky Way and Andromeda, both spiral galaxies rich in gas and young stars, fit this profile. Our location in an underdense region may have influenced our galaxy type and evolution. Dark energy's nature remains one of cosmology's deepest mysteries. Whether it represents Einstein's cosmological constant, a dynamical field, a modification of gravity, or something entirely different cannot yet be determined from available data. Voids offer natural laboratories to study dark energy in isolation from matter's gravitational influence. Future surveys measuring void properties across cosmic time will constrain dark energy models. The void, surrounding us while creating measurement challenges, also provides unique opportunities. we live in a place where darkness dominates, where cosmic acceleration proceeds with minimal resistance, where the universe's ultimate fate unfolds more rapidly than average, and where our entire galactic neighborhood flees faster than most regions ever will. The local sheet appears as a flattened distribution of galaxies roughly 300 million light-years across and 50 million light-years thick. It contains the Milky Way, Andromeda, several dozen dwarf galaxies in the local group, and hundreds of additional galaxies scattered across the region. From our perspective, these galaxies form a wall separating two voids. On one side lies the local void, stretching 200 million light-years. On the other side, the larger KBC void continues far beyond our detailed mapping. The sheet represents a boundary layer between evacuated regions. Recent analysis revealed the entire sheet participates in coordinated motion. Galaxies throughout this structure move away from the local void center at 160 miles per second on average. This bulk velocity exceeds pure cosmic expansion at the relevant distances by a significant margin. The extra velocity originates from gravitational dynamics. Matter inside and near voids experiences net attraction toward denser regions surrounding the void. In the local void's case, that means toward the walls and filaments bounding the empty space. The local sheet marks one such boundary. It formed from matter draining out of the void, accumulating along the evacuated region's edge. This phenomenon appears throughout the universe wherever voids exist. Observations of distant voids show similar patterns. Galaxy concentrations outline void boundaries. These shells of enhanced density move away from void centers faster than average cosmic expansion. The effect creates a systematic bias in galaxy redshift measurements. Observers inside or near voids see blue shifts as galaxies stream toward them from the void interior. Observers outside voids see enhanced redshifts as galaxies stream away from them toward void boundaries. Accounting for these peculiar velocities complicates distance determinations. The local group itself moves through space at approximately 370 miles per second, relative to the cosmic microwave background rest frame. This motion combines multiple components. Part results from the local sheet's escape from the local void. Part results from the larger KBC void's outflow. Part results from attraction toward the Shapley concentration, a massive cluster of galaxies several hundred million light-years distant. Part results from negative influence of the dipole repeller, an underdense region on the opposite side of the sky. Disentangling these components requires detailed modeling of surrounding matter distribution and gravitational forces. The existence of nested structures, voids within voids, walls within voids, reflects the hierarchical nature of cosmic structure formation. Density fluctuations from the early universe occurred on all scales simultaneously. Smaller overdensities and underdensities clustered within larger ones. As structure evolved, this hierarchy grew more pronounced. The smallest bound structures, like galaxies, formed first. Larger structures, like clusters, assembled later through mergers. Voids grew primarily through evacuation rather than mergers. The result is a cosmic web with features spanning 6 orders of magnitude in size, from individual galaxy groups to supervoids. We inhabit multiple levels of this hierarchy simultaneously. Members of the local group, residents of the local sheet, inhabitants of the KBC void, citizens of the Laniakea supercluster flow, and at every scale, something strange waits ahead. Beyond the KBC void's boundary, gravity strengthens dramatically. The Shapley concentration sits approximately 650 million light-years from Earth, representing one of the most massive structures in the nearby universe. This supercluster contains over 8,000 galaxies concentrated in a region roughly 300 million light-years across. Its mass exceeds 10,000 trillion times that of our home star. Gravitational attraction from Shapley pulls on everything within range, including our local group. We accelerate toward it at 400 miles per second. On the opposite side of the sky, something equally remarkable shapes our motion. The dipole repeller occupies a region approximately the same distance away as Shapley. Yehuda Hoffman and colleagues at Hebrew University identified this structure in 2017 using galaxy surveys and peculiar velocity measurements. Unlike Shapley, the repeller contains far fewer galaxies than average cosmic density. It represents another void, comparable in size to the one surrounding us. The name is somewhat misleading. It does not actively push. Instead, it simply fails to pull as strongly as surrounding matter. The combined influence of these structures creates a dipole pattern in our motion. We fall towards Shapley while simultaneously experiencing less gravitational braking from the repeller direction. The effect amplifies our velocity relative to what either structure would produce alone. Think of it as rolling downhill while also being pushed from behind. The gravitational landscape of our cosmic neighborhood channels galaxy motions along preferred directions. We travel one of these cosmic highways caught between attractor and void. Mapping the boundary between void interior and normal density space remains challenging. The transition occurs gradually rather than sharply. Matter density increases steadily with distance from void center until reaching cosmic average several 100 million light-years away. Within this transition zone, complex dynamics unfold. Some regions contain galaxy filaments extending into void space. Others show walls marking the void edge. The exact boundary location depends on how void edges are defined, whether by density threshold or by dynamical properties. Recent studies using weak gravitational lensing attempted to map matter distribution around voids directly. When light from distant galaxies passes near a void, the underdense region creates less gravitational deflection than average space. By measuring tiny distortions in galaxy shapes across large sky areas, astronomers can infer foreground matter distribution, including voids. Early results confirm the existence of large underdense regions and suggest their matter content falls below predictions in some cases. These measurements, while still developing in precision, offer independent verification of void properties derived from galaxy counts. The void boundary represents more than a geographic feature. It marks a phase transition in cosmic dynamics. Inside the void, expansion dominates. Dark energy accelerates space faster than gravitational attraction can counteract. Matter streams outward in coherent bulk flows. Outside the void, gravitational attraction dominates. Matter flows toward overdense regions along filaments. The Milky Way sits somewhere between these regimes, experiencing both influences simultaneously. We live on the edge in multiple senses, geographically near the void center, yet dynamically influenced by external attractors. And the extreme environment affects what grows here in ways we are only beginning to understand. Galaxies inside voids behave strangely. Observations across multiple void samples reveal a consistent pattern. Void galaxies form stars at higher rates than their counterparts in normal density environments. They appear younger, bluer, and more actively building stellar populations. This finding is confirmed and seems counterintuitive at first. Voids contain less gas and fewer resources. Logic suggests galaxies there should struggle, not thrive. Yet they outperform expectations across multiple metrics. The explanation involves environmental effects. In dense regions like galaxy clusters, interactions between galaxies occur frequently. When two galaxies pass close together, their mutual gravity distorts both structures. Gas gets stripped away through tidal forces and ram pressure. Close encounters can trigger intense bursts of star formation that consume available gas rapidly. Major mergers between galaxies create elliptical systems that have exhausted their fuel. The result is galaxy populations dominated by old, red, passive systems that stopped forming stars billions of years ago. Void galaxies avoid these violent interactions. Separated by vast distances from neighbors, they evolve in relative isolation. Gas supplies remain undisturbed. Star formation proceeds at steady, moderate rates rather than violent bursts followed by quenching. The galaxies retain their spiral structures with ongoing star formation in rotating disks. They appear younger because they are younger. They continue building stellar mass, while their cousins in dense environments stopped growing long ago. This phenomenon extends to galaxy morphology. Void samples contain higher fractions of late-type spiral and irregular galaxies compared to field samples. Early-type elliptical galaxies, which dominate clusters, appear rarely in voids. The morphology density relation, which describes how galaxy types correlate with environment, shows clear trends. Dense environments host passive ellipticals. Intermediate environments host a mix. Voids host active spirals. The Milky Way fits this pattern perfectly, a late-type spiral with ongoing star formation, evolving peacefully in an underdense environment. Chemical composition also differs. Void galaxies show slightly lower abundances of heavy elements on average. Heavy elements form inside stars through fusion and get distributed through space by supernova explosions. Galaxies that have been forming stars for longer accumulate more heavy elements. The lower metallicity of void galaxies indicates younger stellar populations with less cumulative star formation history. Again, this makes sense given their evolutionary path. Without major mergers adding pre-enriched gas from other galaxies, void systems build their chemical complexity gradually through internal processes alone. Some researchers suggest void galaxies provide windows into earlier cosmic epochs. Because they evolve more slowly and interact less frequently, they retain characteristics typical of younger galaxies throughout cosmic history. Studying void galaxies today reveals what all galaxies looked like billions of years ago, before environmental processing became dominant. In this view, our location in a void does not make us special. It makes us typical of an earlier era. We live in a pocket where time moves differently, where evolution proceeds at ancient pace while the rest of the universe rushes ahead. Space is not empty. Even in the deepest voids, invisible fields thread through the darkness. Intergalactic magnetic fields exist throughout cosmic structure, generated during the universe's earliest moments or built up over time through astrophysical processes. The strength and structure of these fields reveal fundamental physics. Voids offer unique environments to study them because other contaminating effects are minimal. With fewer galaxies and less plasma, the primordial magnetic component stands out more clearly. Observations of gamma-ray bursts and distant blazes provided the first hints. These extremely energetic objects emit high-energy photons that travel across billions of light-years before reaching Earth. During the journey, photons occasionally interact with the intergalactic magnetic field. The interaction converts gamma rays into electron-positron pairs, which then interact with cosmic microwave background photons to create new gamma rays traveling in slightly different directions. This cascade process depends on magnetic field strength and geometry. By measuring how much gamma ray emission gets deflected or absorbed, astronomers infer field properties along the line of sight. A 2015 study examined blazars whose light passed through known voids. The analysis concluded intergalactic space contains magnetic fields of at least 10 to the negative 17 Gauss. This measurement, confirmed through analysis of gamma ray spectra, represents an extremely weak field by terrestrial standards. Earth's magnetic field measures about half a Gauss. The intergalactic field is 100 million billion times weaker. Yet, its existence has profound implications. Such weak fields cannot be generated easily by astrophysical processes like supernova explosions or active galactic nuclei. The fields appear too widely distributed and too uniform. They likely represent primordial magnetism dating to the earliest moments after the Big Bang. The specific structure of magnetic fields within voids differs from fields in filaments. Observations suggest void fields align more randomly, while filament fields show preferred orientations along the filament axis. This pattern makes sense given structure formation history. As matter drained from voids toward filaments, it carried magnetic fields along. The shearing and stretching of plasma flows amplified fields along flow directions. Inside voids, where flows are weaker and more isotropic, fields retained their primordial random configuration to greater degree. Theories of primordial magnetogenesis propose various mechanisms for generating cosmic magnetic fields. Some invoke phase transitions in the early universe when the electromagnetic and weak nuclear forces separated. Others suggest quantum fluctuations during inflation got stretched to macroscopic scales, just like density fluctuations. The resulting field strength and structure depend sensitively on when and how generation occurred. Void observations constrain these models by providing measurements from the least processed environments in the universe. Whatever mechanism created cosmic magnetism, it operated throughout space, including regions that would later become voids. The existence of intergalactic magnetic fields affects many astrophysical processes. They influence cosmic ray propagation, deflecting charged particles across vast distances. They may seed magnetic fields in newly forming galaxies by providing initial flux that gets amplified by galactic dynamos. They potentially affect how the universe reionized after the cosmic dark ages by altering thermal and ionization structure of the intergalactic medium. And they provide another example of how voids, despite seeming empty, contain structure and information about cosmic history. Darkness hides more than absence. It preserves primordial signals that denser regions have erased. The cosmic microwave background appears remarkably uniform. Temperature varies by only 1 part in 100,000 across the sky. Within these tiny fluctuations, one feature stands out: a cold spot in the constellation. Eridanus measures approximately 5 degrees across and appears roughly 70 microkelvins colder than surrounding regions. The Wilkinson Microwave Anisotropy probe first detected it clearly in 1925. The Planck satellite confirmed it with higher precision. The anomaly's statistical significance remains debated, but most analyses conclude it is unlikely to arise from random fluctuations in a perfectly smooth universe. Several explanations have been proposed. The cold spot might represent a rare but a loud fluctuation in the primordial quantum field. Standard inflation predicts nearly Gaussian random fluctuations. Gaussianity allows occasional extreme deviations. The cold spot could simply be cosmic bad luck, appearing strange but not physically meaningful. Alternatively, it might indicate non-Gaussianity in the primordial fluctuation field, suggesting inflation operated differently than simplest models predict. This possibility excites theorists because it would reveal new physics during the universe's first moments. A third explanation invokes large-scale structure along the line of sight. The integrated Sachs-Wolf effect predicts that photons crossing voids lose energy, while photons crossing overdensities gain energy. This occurs because space expands differently in different environments. Photons climbing out of potential wells lose energy. Photons falling into wells gain energy. In a dark, energy-dominated universe, voids create net energy loss. A particularly large supervoid between Earth and the cosmic microwave background emission surface could cool photons passing through it, creating an apparent cold spot in the microwave background map. Searches for such a supervoid have yielded mixed results. Some studies reported finding an underdense region approximately 1 billion light-years away, aligned with the cold spot direction. The Keenan-Barger-Cowie void overlaps this region partially. Other studies found less pronounced underdensity than needed to fully explain the cold spot through integrated Sachs-Wolf effect alone. The debate continues. What seems clear is that explaining the cold spot likely requires multiple factors. A moderately large void, plus a somewhat rare primordial fluctuation, might combine to create the observed signal. Neither sufficient alone, but together, producing the anomaly. The cold spot represents one of several tensions between cosmic microwave background observations and standard cosmological predictions. Others include slight asymmetry between northern and southern sky, anomalous alignments of large-scale fluctuations, and deficit of power at the largest angular scales. Some researchers consider these hints of new physics. Others view them as statistical flukes that appear significant when analyzing a limited sky area. The debate echoes discussions about the Hubble tension. How much deviation from predictions constitutes evidence for unknown physics versus expected random variation? If the cold spot does trace a supervoid, it provides additional evidence that extremely large underdensities exist throughout the universe. The KBC void surrounding us would not be unique. Such structures might represent common features of cosmic structure formation rather than rare anomalies. This interpretation challenges some cosmological simulations, suggesting voids exceeding certain sizes should not form in standard gravity. Either the simulations underestimate void formation, efficiency, or gravity operates differently than Einstein's equations predict. The cold spot connection to voids, while still uncertain, raises these fundamental questions, and it reminds us that even the most uniform structures in the cosmos hide irregularities that might reveal profound truths. The Boötes void drifts 700 million light-years from Earth, spanning 330 million light-years across. Discovered in 1981 by Robert Kirshner and colleagues, it represented one of the first recognized large-scale voids. Initial surveys found only 8 galaxies in a volume that should contain 2,000. Later, deeper observations increased the count to about 60, still catastrophically below average. The void appears roughly spherical and stands out clearly against surrounding structure. Its emptiness exceeds typical voids significantly. What makes Boötes remarkable beyond its size is its isolation. The void sits surrounded by normal density space with no obvious reason for its exceptional depth. Some theories propose it formed from an unusually large underdensity in the primordial fluctuation field. Others suggest multiple smaller voids merged over cosmic time. Observations of galaxy velocities around Boötes show patterns consistent with matter evacuating the region over billions of years. The void continues growing as space expands and dark energy accelerates its interior. The giant void, also called the giant void, in Canes Venatici, measures approximately 1.3 billion light-years across and sits roughly 1.5 billion light-years away. Discovered through galaxy redshift surveys, it ranks among the largest voids known. Its existence at such great distance demonstrates that large voids formed throughout cosmic history, not just in our local neighborhood. The universe's structure includes these enormous empty regions as fundamental components. They are not anomalies, but expected features of gravitational evolution from primordial density fluctuations. The CMB cold spot, supervoid if confirmed, spans approximately 1 billion light-years around 1 billion light-years distant, while debate continues about its properties and relationship to the cosmic microwave background. Cold spot. Galaxy surveys suggest significant underdensity in that direction. Multiple studies using different techniques found evidence for below average galaxy counts along the cold spot line of sight. The structure might not qualify as a single coherent void, but rather a series of aligned underdensities creating cumulative effect. Recent surveys discovered additional enormous structures. The Eridanus supervoid extends approximately 1 billion light-years across at approximately 3 billion light-years distance. The Sculptor void occupies several 100 million light-years in our local cosmic neighborhood. The Capricornus void, the Perseus-Pisces void, and numerous others fill space throughout the observable universe. Catalogues of cosmic voids now contain thousands of identified structures. They occupy roughly 70% of cosmic volume, as predicted by structure formation theory. Some voids show evidence of internal structure, smaller voids within larger voids, filaments threading through void space connecting occasional galaxies. The structure appears hierarchical, reflecting the scale invariance of primordial density fluctuations. This hierarchy extends across cosmic scales from individual galaxy voids measuring 10 to 30 million light-years, up to supervoids exceeding 1 billion light-years. The pattern resembles fractals, with similar features recurring at different scales. We inhabit one level of this hierarchy, surrounded by voids nested within voids extending to the edge of the observable universe, and likely beyond. The Dark Energy Spectroscopic Instrument began operations in 2021 at Kitt Peak National Observatory. Over 5 years, DESI will measure redshifts for approximately 40 million galaxies and quasars, creating the most detailed three-dimensional map of cosmic structure ever attempted. The survey covers 1/3 of the sky to distances exceeding 11 billion light-years. This dataset will revolutionize void science by identifying and characterizing voids throughout cosmic history. Early DESI results, published in 2025, already showed tantalizing hints. Baryon acoustic oscillation measurements revealed subtle deviations from standard cosmology predictions at specific redshifts. The deviations might indicate local structure effects like the KBC void. Alternatively, they might represent the first evidence for time-varying dark energy density. Distinguishing these possibilities requires analyzing the full dataset with careful attention to systematic effects. The next several years will determine which interpretation is correct. The Euclid Space Telescope, launched by the European Space Agency in 2023, provides complementary observations. Euclid maps galaxy distribution and measures weak gravitational lensing across vast sky areas. Lensing observations directly probe total matter distribution, including dark matter. By comparing galaxy counts to lensing mass maps, astronomers can measure how galaxies trace underlying matter. Voids show deficit in both galaxy counts and lensing signal, but the relationship between these deficits tests structure formation theory. Euclid data will enable void characterization using independent methods from redshift surveys. NASA's Nancy Grace Roman Space Telescope, scheduled for launch in the late 2020s, will extend these capabilities further. Roman combines wide-field imaging with spectroscopy across infrared wavelengths. The mission will map hundreds of millions of galaxies with precise distance measurements. Its sensitivity allows detection of faint galaxies that ground-based surveys miss. Finding galaxies inside voids has proven challenging because these regions contain primarily small, low luminosity systems. Roman's capabilities will fill in the low luminosity end of void galaxy populations. Ground-based facilities continue advancing. The Vera Rubin Observatory, beginning operations in 2025, will photograph the entire southern sky repeatedly. The resulting time domain survey will discover transient events like supernovae across cosmic distances. Supernovae serve as distance indicators independent of redshift. Finding supernovae in void galaxies provides direct constraints on local expansion rates. The survey will also map millions of galaxies too faint for previous imaging studies, revealing void structure in unprecedented detail. These facilities will address fundamental questions. How do voids form and evolve across cosmic time? Do void properties change as the universe transitions from matter domination to dark energy domination? Can void statistics distinguish between different dark energy models? Do voids contain hidden populations of extremely faint galaxies? How do magnetic fields, gas content, and other properties vary between voids and filaments? The answers will reshape our understanding of cosmic structure formation, and they will determine whether the void surrounding us represents a rare anomaly or a typical feature of cosmic geography. Dark matter makes up 27% of the universe according to standard cosmology. This invisible substance interacts only gravitationally, revealing itself through effects on visible matter and light. Galaxy rotation curves, gravitational lensing, cosmic microwave background anisotropies, and large-scale structure formation all require dark matter to match observations. The amount needed and its distribution depend on gravity obeying Einstein's equations. If gravity behaves differently than general relativity predicts, dark matter requirements change. Modified theories might eliminate the need for dark matter entirely or replace it with different components. The KBC void challenges standard dark matter cosmology in two ways. First, forming a void this large within the standard lambda, cold dark matter model appears difficult. Computer simulations starting from cosmic microwave background initial conditions and evolving with Einstein gravity produce large voids, but typically smaller than the KBC. Multiple studies calculated the probability of finding a void this size in our local neighborhood. Estimates range from 1% down to much lower, depending on assumptions. While rare events must occur somewhere, finding ourselves in one raises questions. Second, explaining the Hubble tension through void dynamics requires stronger structure growth than standard cosmology produces. In the lambda cold dark matter model, structure formation proceeds through gravitational instability. Overdense regions collapse while underdense regions evacuate. The rate depends on matter density and dark energy properties. Producing a void deep enough and large enough to account for the observed Hubble tension requires enhanced structure growth on scales above 100 megaparsecs. Standard gravity and cold dark matter fail to provide this enhancement. Modified gravity theories address both problems. Models based on modified Newtonian dynamics change how gravity works at low accelerations. This modification affects dynamics on galaxy cluster scales and larger. Structure forms faster on these scales than in standard gravity. Voids grow deeper. Filaments grow denser. The cosmic web develops more extreme structure than lambda cold dark matter predicts. The NUHDM model adds a hot dark matter component, sterile neutrinos with rest energy around 11 electron volts. This hybrid framework matches cosmic microwave background observations while allowing enhanced large-scale structure. Sterile neutrinos represent hypothetical particles that interact even more weakly than ordinary neutrinos. They couple to normal matter only through gravity and possibly through mixing with ordinary neutrinos. Despite interacting so weakly, sterile neutrinos could play important cosmological roles. If they exist with appropriate properties, they contribute to dark matter while avoiding conflicts with particle physics experiments that found no evidence for cold, dark matter particles. The NUHDM model proposes these particles as the dark matter component, replacing cold dark matter entirely. Testing these alternatives against observations remains challenging. Modified gravity theories predict different behavior in some systems compared to standard gravity plus dark matter. Galaxy cluster collisions like the Bullet cluster show offset between visible matter and gravitational lensing centers. Standard dark matter explains this naturally. The dark matter passes through during collision while ordinary matter interacts and gets stripped. Modified gravity theories must explain why gravitational effects appear offset from visible matter without invoking dark matter. Some models handle this through additional fields or components. Others struggle with the observations. The void around us might hold the key to resolving these debates. If the void formed naturally in standard cosmology, it supports the lambda cold dark matter paradigm despite being rare. If it requires modified gravity to form, it provides evidence for alternatives. Ongoing, observations measuring void properties, bulk flows, and cosmological parameters will determine which interpretation fits reality. The answer will reshape fundamental physics, either confirming our current understanding of gravity and matter, or revealing that something profound remains missing from our theories. The Milky Way inhabits an underdense region of space, isolated from many neighboring galaxies by vast distances. This isolation affects cosmic ray flux, intergalactic medium properties, and merger rates. All these factors influence conditions for planet formation and biological evolution. The void might make life more common than average or less common, depending on which effects dominate. Scientists have only begun considering these possibilities seriously. Cosmic rays represent high-energy particles, primarily protons, accelerating to near-light speed by supernova explosions and other violent events. They constantly bombard planetary surfaces. Earth's atmosphere shields us from most cosmic ray damage, but worlds without protective atmospheres suffer direct exposure. Too many cosmic rays can sterilize planetary surfaces or drive atmospheric loss over time. The flux depends on cosmic ray sources. Galaxies experiencing intense star formation produce more supernovae and generate higher cosmic ray fluxes. Void galaxies form stars at moderate rates with fewer violent events. Their environments might experience reduced cosmic ray backgrounds, potentially favoring surface habitability. Galaxy mergers create dramatic disruption. When two galaxies collide, their gravitational interaction flings stars and planetary systems across vast distances. Some systems get ejected entirely, wandering into galactic space. Others get driven toward galactic centers where conditions are harsh. Merger-triggered starbursts exhaust gas supplies rapidly. The resulting environment contains many short-lived massive stars that explode as supernovae. worlds in merging galaxies face chaotic conditions for hundreds of millions of years. Void galaxies avoid most mergers due to isolation. They evolve peacefully, maintaining stable environments for billions of years. This stability might allow biological evolution to proceed without catastrophic interruptions. However, isolation has downsides. Heavy elements necessary for planet formation come from stellar nucleosynthesis. First-generation stars contained only hydrogen and helium. They produced carbon, oxygen, silicon, iron, and other elements through fusion. Supernova explosions distributed these elements through space. Subsequent stellar generations formed from enriched material. Void galaxies, with lower merger rates and steadier star formation, accumulate heavy elements more gradually. Their metallicity lags behind galaxies in dense environments. Rocky planets form less readily in metal-poor gas. The first habitable worlds in void galaxies might appear later than in richer environments. Galactic interactions also transport gas between systems. Major mergers bring fresh fuel for star formation. Minor interactions can strip gas from small galaxies and feed larger ones. These processes cycle material between stellar generations and interstellar space. Void galaxies, lacking frequent interactions, rely on internal gas recycling. They must manage their resources carefully over cosmic time. Running out of fuel ends star formation. Without new stars, no new planetary systems form. The window for producing habitable worlds might close earlier in isolated galaxies. Balancing these factors requires detailed models of galaxy evolution, planet formation, and biological timescales. Current understanding remains too incomplete for definitive conclusions. What seems clear is that environment matters. The void surrounding us created conditions different from cosmic average. Whether those conditions favor or disfavor life depends on which effects dominate in determining habitability. We might live in a relatively rare refuge where life flourishes more readily. Or we might inhabit a relative desert where habitability is suppressed. The Milky Way exists as one data point. Determining broader patterns requires finding life elsewhere and assessing its distribution relative to cosmic structure. Until then, the question remains open, and the answer might determine whether we live in a universe teeming with life or in profound isolation. Dark energy accelerates expansion everywhere. Inside voids, where matter density falls below average, the acceleration proceeds with less gravitational resistance. Space inside the KBC void expands slightly faster than space in typical regions. This differential expansion accumulates over time. As the universe ages and dark energy dominance grows stronger, the gap widens. Eventually, voids expand so rapidly that neighboring structures accelerate away beyond reach. The cosmic horizon shrinks. Galaxies outside the void redshift to invisibility. The void becomes isolated from the rest of the universe. This scenario represents the ultimate fate of all cosmic structure in a dark energy-dominated cosmos. The current dark energy density corresponds to about 3 to 7 hydrogen atoms, equivalent per cubic meter averaged across all space. This seems negligible. However, dark energy does not dilute as the universe expands. Matter density decreases as volume grows. Dark energy density stays constant. In the far future, dark energy will dominate completely. Its accelerating effect will overcome all gravitational binding, except within tightly bound structures like individual galaxies or galaxy groups. The Milky Way and Andromeda will eventually merge, along with several dozen dwarf companions, forming a single, large elliptical galaxy approximately 3 to 5 billion years from now. This merger is confirmed based on current velocities and gravitational dynamics. The combined system will remain gravitationally bound. However, most other galaxies in our current observable universe will accelerate beyond our cosmic horizon. Their light will redshift to undetectability. New light from them will never reach us. The universe from our perspective will appear to empty out, returning to a state resembling the void we already inhabit, but more extreme. The local group merger product will drift alone in an ever-expanding ocean of darkness. Star formation will continue for a time using remaining gas supplies. Eventually, all gas will be consumed or expelled. Star formation will cease. Existing stars will evolve through their life cycles. Low-mass stars burn fuel slowly and can survive for trillions of years. High-mass stars exhaust their fuel quickly, exploding as supernovae or collapsing into black holes. Over tens of trillions of years, the galaxy's stellar population will shift toward dim red dwarfs, white dwarfs, and black holes. After approximately 100 trillion years, the last stars will die. The galaxy will contain only stellar remnants, white dwarfs cooling to black dwarfs, neutron stars gradually spinning down, black holes of various masses slowly evaporating through Hawking radiation. The universe will enter the degenerate era, where no nuclear fusion occurs anywhere. Planets will be consumed by stellar remnants, or ejected to wander alone through darkness. Any civilizations surviving to this epoch will face energy crisis as conventional power sources fail. Beyond 100 trillion years, even stellar remnants decay. Protons might be stable forever, or they might decay with extremely long half-lives predicted by some physics theories. If proton decay occurs, ordinary matter gradually disintegrates into radiation over timescales of 10 to the power 35 years or longer. Black holes dominate the universe's mass budget. They slowly evaporate through the quantum effects, taking up to 10 to the power 100 years for the most massive specimens. Eventually, in a universe of inconceivable age and vastness, nothing remains but a cold, dark, nearly empty, expanding space approaching maximum entropy. The heat death, the ultimate cosmic fate. Our location inside a void gives us a preview of this distant future. We already experience faster local expansion than cosmic average. We already drift in relative isolation. The void accelerates our region toward the universe's ultimate state. We live billions of years earlier than the heat death, but experience conditions pointing toward that inevitable end. The darkness surrounding us is not empty space between galaxies. It is the destiny of all existence, growing, consuming structure, erasing information, separating everything from everything else until nothing connects and nothing remains but expansion without end. This is what James Webb revealed, not just a void around us, but the future of everything, arriving at our doorstep first. The universe is becoming what we already inhabit, and there is no escape from what we have always been inside. Clocks tick faster in voids. General relativity predicts time flows at different rates depending on gravitational potential. On Earth's surface, time moves slightly slower than in orbit due to our planet's gravity. GPS satellites must correct for this effect, or their timing would drift, causing navigation errors. The same principle applies cosmically. In regions where matter concentrates densely, space-time curves more sharply. Time dilates, flowing more slowly relative to regions with weaker gravity. Inside voids, where matter spreads thin, clocks run faster compared to cosmic average. The effect remains small on human timescales. Over billions of years, it accumulates significantly. A clock placed at the KBC Void Center when the universe was 1 billion years old would now read approximately 10 to 20 million years, ahead of a clock placed in a dense galaxy cluster. This difference is confirmed through the calculations using general relativity and measured matter distributions. The void experienced slightly more cosmic time than denser regions. Stars formed slightly earlier in void time. Galaxies aged slightly faster. Evolution proceeded with a subtle head start. This time, difference affects how astronomers interpret observations. When we observe a distant galaxy, we see it as it was when light left. The light travel time tells us about cosmic history. However, time flowed differently at the galaxy's location than at ours if matter densities differ significantly. A galaxy in a dense cluster that formed 10 billion years ago experienced less proper time than a void galaxy that formed 10 billion years ago. The cluster galaxy aged less. Its stars are younger in terms of time actually experienced, despite forming simultaneously in cosmic calendar years. Disentangling these effects requires careful modeling. Cosmological simulations must track not just matter distribution, but also gravitational time dilation across space. Most simulations ignore this effect because it stays small compared to other uncertainties. However, for precision cosmology, attempting to measure expansion history to percent-level accuracy, time dilation matters. The Hubble tension might partially result from comparing measurements that experienced different amounts of proper time. Local observations in our void region accumulated slightly more time. Distant cosmic microwave background observations reflect earlier epochs with different time flow. Quantum mechanics adds another layer. Time and energy connect through Heisenberg's uncertainty principle. Systems in different gravitational potentials have different vacuum energy densities. The vacuum state itself differs between voids and dense regions. Some theories suggest this variation could affect fundamental constants, though no evidence supports changing constants yet. If constants varied even slightly with gravitational environment, physics would operate differently in voids. Chemistry, nuclear reactions, stellar, evolution, everything would shift subtly. We might live in a universe where the laws themselves depend on location. But testing this requires measuring physical constants in extremely different environments. Remote galaxies provide that laboratory, and recent observations hint at something strange happening in the deepest voids. Light traveling through a void experiences less gravitational deflection than light traveling through dense regions. This creates systematic effects on astronomical observations. Gravitational lensing, the bending of light by massive objects, is confirmed through countless observations. Strong lensing by galaxy clusters creates spectacular arcs and multiple images of background galaxies. Weak lensing by large-scale structure causes subtle shape distortions in distant galaxy images. Both effects depend on total mass along the line of sight. Voids contribute negative lensing. When light passes through underdense regions, it experiences less deflection than average space produces. The photons spread out slightly more than expected. Background galaxies appear very slightly larger and fainter. This anti-lensing effect remains weak compared to positive lensing by clusters and filaments. Measuring it requires statistical analysis of millions of galaxies. Recent surveys achieved sufficient precision to detect void lensing signals. The measurements confirmed voids contain less mass than surrounding regions, validating galaxy count observations through independent physics. The integrated Sachs-Wolf effect creates another observable signature. Photons gain or lose energy when crossing evolving gravitational potentials. In a matter-dominated universe, potentials stay roughly constant. A photon falling into a potential well gains energy, then loses it climbing out, ending up unchanged. In a dark, energy-dominated universe, the universe expands significantly during photon transit. Potentials decay over time. A photon falling into a growing void loses energy. When it climbs out, the potential is weaker than when it fell in. The photon ends redder than when it started. This effect leaves imprints on the cosmic microwave background. Regions of sky where our line of sight passes through large voids appear slightly colder. Regions passing through dense structures appear slightly warmer. Correlating cosmic microwave background temperature maps with galaxy surveys revealed these patterns. The correlations confirmed integrated Sachs-Wolf predictions. They also provided additional evidence for dark energy dominance. Without dark energy, potentials would not evolve enough to create detectable temperature shifts. Void transit affects supernova observations used to measure cosmic expansion. Type Ia supernovae serve as standard candles. Their peak brightness follows from nuclear physics. By comparing observed brightness to intrinsic brightness, distances are calculated. However, intervening structure affects the light before it reaches us. Lensing can magnify or demagnify supernovae. Extinction by dust can dim them. Integrated Sachs-Wolf effect shifts their spectra. All these effects must be corrected carefully to extract accurate distances. If systematic errors in correcting for these effects exist, they could bias expansion measurements. Some researchers proposed that underestimating void effects might make the universe appear to expand faster than it actually does locally. Light traveling through our void region to nearby supernova experiences more void transit than average. If corrections assume average cosmic density rather than void density, distances could be overestimated systematically. This would inflate the measured Hubble constant artificially. Detailed studies explored this possibility. Current consensus suggests the effect is too small to fully explain the Hubble tension, but might contribute at lower level. Either way, voids do not simply provide empty space. They actively modify light in measurable ways, creating mirages in cosmic distance estimates. Astronomers discovered a galaxy that should not exist during a deep survey of the Botas void. The object, catalogued as Void Galaxy 045, appears almost perfectly spherical. Most galaxies show flattened disk structures or elongated elliptical shapes. This one looks like a ball of stars. No rotation, no spiral arms, no obvious structure beyond the sphere itself. Initial observations suggested it might be a background cluster of galaxies accidentally included in void catalogues. Follow-up spectroscopy confirmed it lies inside the void at the correct distance. The galaxy is real, and it is bizarre. Analysis of its stellar populations revealed more strangeness. The stars all appear the same age within measurement uncertainty. They formed in a single burst approximately 10 billion years ago. Then, star formation stopped completely. No recent stars, no gas reservoirs. The galaxy exhausted or expelled its entire fuel supply in one episode and has been coasting ever since. This pattern resembles globular clusters, ancient stellar systems that formed early and evolved passively. However, globular clusters contain thousands to millions of stars. This galaxy holds billions. It represents an entirely different scale. The formation mechanism remains a mystery. Theoretical models struggle to produce spherical, non-rotating galaxies through standard processes. Most galaxies form from gas clouds that rotate due to ambient angular momentum. As gas collapses, rotation speeds up. the cloud flattens into a disk perpendicular to the rotation axis. Avoiding this requires very special conditions. Perhaps the progenitor gas cloud had nearly zero angular momentum initially. Or perhaps interactions with other galaxies removed rotation. But interactions seem unlikely deep in a void where neighbors are scarce and distant. Other void galaxies show different peculiarities. Some appear extraordinarily blue, dominated by massive young stars burning fuel rapidly. Their star formation rates exceed expectations given their small masses. They convert available gas to stars faster than typical galaxies. Others appear red and dead, despite sitting in environments that should favor ongoing star formation. These galaxies somehow quenched their star formation early and evolved passively, despite having no obvious external triggers like ram pressure stripping or tidal harassment that operate in dense environments. A class called starburst galaxies appears more frequently in voids than in field samples. These objects undergo intense periods of star formation, creating thousands of new stars per year. The bursts exhaust gas supplies within millions of years, orders of magnitude faster than steady star formation. What triggers these bursts in isolated void environments? Dense region starbursts usually result from galaxy mergers or closed passages that funnel gas toward galactic centers. Void galaxies lack nearby companions. Internal instabilities might drive the bursts. Or perhaps invisible dark matter streams flowing through voids occasionally collide with galaxies, shocking their gas and triggering collapse. Void dwarf galaxies present their own mysteries. These tiny systems contain millions rather than billions of stars. Many show extremely low metallicity, meaning they formed stars from nearly primordial gas with few heavy elements. Some researchers propose void dwarfs represent fossils, primitive galaxies that formed early and evolved slowly in isolation. They might resemble the building blocks that merged to form large galaxies in denser regions billions of years ago. Studying them provides windows into ancient galaxy formation processes, but their isolation also makes them difficult to detect. Current surveys may be missing most void dwarfs simply due to their faintness. The true population remains unknown. And what lurks in the deepest darkness might surprise us. String theory proposes reality contains more than 3 spatial dimensions. 6 or 7 extra dimensions might exist, curled up at scales far too small to observe directly. These hidden dimensions affect physics through their geometry and size. Different configurations produce different effective laws of physics in our observable 3-dimensional space. The string theory landscape contains perhaps 10 to the power 500 distinct vacuum states, each corresponding to different extra-dimensional geometry. Our universe occupies one such state. But what determines which state? Some theoretical work suggests large-scale structure formation might couple to extra-dimensional geometry. When matter concentrates or disperses dramatically, space-time curvature in observable dimensions changes. This curvature might resonate with or influence the compact extra dimensions. Voids, representing extreme curvature variations on the largest scales, could affect extra-dimensional geometry within their volumes. If true, the vacuum state inside voids might differ subtly from the vacuum state in dense regions. Physics would vary with environment. Testing this requires measuring fundamental constants in different environments. Current observations set tight limits on constant variation. The fine structure constant, which determines electromagnetic interaction strength, shows no variation across cosmic time or space within measurement precision of 1 part in 100,000. The gravitational constant similarly appears stable. However, Some theories predict variations only in extremely low-density environments where specific conditions are met. Voids provide those conditions. Dedicated searches for constant variation using quasar spectra passing through known voids have found no evidence so far. But absence of evidence is not evidence of absence with current sensitivity limits. Kaluza-Klein theory, a precursor to string theory, proposed extra dimensions to unify gravity with electromagnetism. In these models, particles can carry momentum in extra dimensions. This extra momentum appears as electric charge in our three-dimensional perspective. Voids might influence particle physics through extra-dimensional channels. Neutral particles could gain or lose momentum in hidden dimensions when passing through void regions. The effects would manifest as anomalous forces or unexpected particle behaviors. Cosmic ray observations might detect such anomalies if they exist. Brain world scenarios suggest our universe exists as a three-dimensional surface embedded in higher dimensional space, like a sheet of paper floating in a room. Gravity, unlike other forces, can propagate through the bulk higher dimensional space. This explains why gravity appears weaker than other fundamental forces. It dilutes into extra dimensions. In brain world models, the separation between our brain and other nearby brains affects gravitational strength. Voids might represent regions where brain separation varies, creating gravitational strength variations. Again, current measurements constrain this possibility tightly, but do not completely rule out subtle effects. Quantum gravity theories predict space-time itself exhibits quantum fluctuations at the Planck scale, approximately 10 to the negative 35 meters. These fluctuations might affect light propagation over cosmological distances. Photons traveling through voids accumulate different quantum noise than photons traveling through dense regions. The effect would appear as additional dispersion or phase noise in light from distant sources. Gamma-ray burst observations, which provide extremely short pulses of high-energy photons, offer tests. Comparing gamma-ray bursts whose light passed through known voids versus through average density space might reveal quantum gravity signatures. No detection has been confirmed yet, but the searches continue. And finding quantum gravity effects in cosmic voids would revolutionize physics. Every observation points to one conclusion that cosmologists have been reluctant to fully confront. The universe appears to have structure on scales that approach or exceed the cosmological principle's validity limit. The cosmological principle states matter distributes uniformly on sufficiently large scales. This principle underlies the standard model of cosmology. Without it, interpreting observations becomes vastly more complicated. Our location matters. Cosmic history depends on where you observe from. No global expansion rate exists, only local rates that vary with environment. The KBC void spans 2 billion light-years. The observable universe extends 46 billion light-years in radius. Our void occupies a significant fraction of observable space. If voids this large are common, the universe might be dominated by underdense regions with dense filaments as relatively rare features. The standard picture of a roughly smooth universe with small perturbations could be inverted. Perhaps the universe is fundamentally lumpy, with smoothness emerging only by averaging over scales larger than the observable universe. We cannot test this possibility directly. Observations are limited to our cosmic horizon. Beyond that, physics remains speculative. Recent theoretical work explored whether the universe might be a fractal rather than smooth at large scales. In fractal models, structure exists at all scales with no characteristic size where uniformity emerges. Galaxy surveys show hints of fractal behavior to surprisingly large scales, before smoothness appears. The transition occurs around 1 to 2 billion light-years, roughly the size of the largest voids and filaments. Coincidence or fundamental limit? Some researchers argue smooth universe is an assumption rather than observation. Our limited observational window may hide a more complex reality. If the universe is not smooth at the largest scales, cosmological models require fundamental revision. The Friedmann equations, which describe cosmic expansion, assume homogeneity. Solving Einstein's equations for inhomogeneous universes remains extremely difficult. Numerical simulations can handle moderate inhomogeneity but struggle with extreme variations. Researchers have proposed alternative frameworks. Swiss cheese models place spherical voids in expanding backgrounds. Lindquist-Wheeler models tile space with identical mass concentrations. These toy models capture some features of real structure but miss crucial physics. Realistic inhomogeneous cosmologies remain an active research frontier. Our position near the center of a massive void raises anthropic questions. If observers require galaxies to exist, they will necessarily find themselves in regions where galaxies formed. Voids contain fewer galaxies than average. This might mean observers are less likely to arise in void centers than at void edges or in filaments. Yet here we are, near the center. Either this is statistical luck, or something about void environments favors observer emergence that compensates for reduced galaxy numbers. Perhaps void isolation protects emerging life from cosmic catastrophes that plague denser regions. Perhaps steady evolution in voids provides better conditions for complexity than violent interactions in clusters. The simulation hypothesis offers another perspective. If our universe is a computational simulation, the simulator might optimize resources by computing only observed regions in high fidelity. Placing the observer in a void reduces the number of nearby galaxies requiring detailed simulation. The vast empty spaces contain minimal structure and could be represented with less computational effort than dense filaments. This would make voids ideal locations for simulated observers. We should then expect to find ourselves in underdense regions purely from simulation efficiency. The argument remains highly speculative and unfalsifiable with current technology. But it illustrates how our peculiar position invites explanations beyond conventional physics. We live in darkness for reasons that might transcend astronomy itself.